The year is 1933. In a factory tucked away in Derby, England, something extraordinary is taking shape. While most of Europe tries to forget the horrors of the Great War, a handful of engineers are hunching over blueprints in dimly lit workshops, sketching out an engine that will one day become legend. They don't know it yet, but what they're building will determine whether freedom survives the coming darkness. This is the story of the Rolls-Royce Merlin, an engine that almost failed before it ever flew, that killed test pilots, that pushed a company to the brink of bankruptcy, yet somehow became the beating heart of victory itself. Let's rewind to understand how we got here. Rolls-Royce wasn't always synonymous with aircraft engines. The company built its reputation on luxury automobiles, machines of refinement and elegance. But Henry Royce, the engineering genius behind the brand, saw something others didn't. He understood that the future of warfare wouldn't be decided on battlefields alone, but in the skies above them. By the early 1930s, aviation technology was evolving rapidly, but most engines still couldn't deliver reliable power at high altitudes where the air grew thin and cold. Royce believed he could solve this problem, and he was willing to bet everything on it. The project that would become the Merlin started with a designation that revealed nothing: PV-12, Private Venture 12, no government funding, no military contracts, just Royce's obsession with creating something perfect. He died in 1933, but his spirit infused every decision the team made. They weren't interested in building an adequate engine, or even a good one. They wanted to build the best engine anyone had ever seen. That ambition would nearly destroy them. Inside the Merlin's design was a level of sophistication that bordered on reckless. We're looking at a V12 configuration, 12 cylinders arranged at a 60-degree angle, each one feeding into a liquid cooling system that had to maintain precise temperatures under impossible conditions. The displacement was enormous, 27 liters, roughly the size of a modern truck engine crammed into an aircraft power plant. But size alone wouldn't win wars. The real innovation lay in how the Merlin breathed. The supercharger was the key to everything. This centrifugal compressor forced air into the cylinders at pressures that let the engine maintain power even when climbing to altitudes where other engines choked and died. At sea level, the Merlin produced over 1,000 horsepower. Push it to 16,000 feet, and it still delivered crushing force when pilots needed it most. Every valve, every piston, every cooling passage was engineered to extract maximum performance from every drop of fuel. On paper, it was a masterpiece. In reality, it was a death trap. The early Merlin engines didn't just underperform, they killed. Test pilots who climbed into aircraft powered by these early versions were gambling with their lives every single time they took off. The cooling system, so elegant in theory, turned into a nightmare in practice. Glycol coolant would superheat without warning. Lines would rupture mid-flight, engines would seize, leaving pilots with nothing but the sound of wind and their own terror as they tried to glide crippled aircraft back to Earth. The connecting rods, those vital links between the pistons and the crankshaft, snapped under stress. But the worst failures were the bearings. Imagine you're 5 miles above the English countryside, traveling at 300 miles per hour, when suddenly the engine locks up. No sputtering, no gradual loss of power. Just instant, deadly silence. For the men who survived these failures, the experience left scars that never fully healed. For those who didn't, their deaths haunted the engineers who had built the machines that betrayed them. Rolls-Royce threw everything they had at solving these problems. Engineers worked shifts that stretched into the early morning hours, redesigning components, testing new materials, pushing themselves to the edge of collapse. They reformulated lubricants. They experimented with exotic alloys. They tore apart failed engines and studied the carnage, looking for clues about what had gone wrong. The pressure was immense, not just from the company's leadership, but from history itself. By 1938, the world was sliding toward war. Hitler's Germany was rearming at a terrifying pace. the Luftwaffe was becoming the most formidable air force on the planet. Britain's Royal Air Force desperately needed fighters that could match German aircraft, but those fighters needed engines that worked. The Merlin was Britain's best hope, yet it remained stubbornly unreliable. Every failed test flight felt like another nail in the coffin of British air power. Then, in a series of breakthroughs that seemed almost miraculous, the pieces fell into place. New metallurgical techniques solved the bearing failures. A redesigned cooling system finally tamed the overheating that had plagued earlier models. Manufacturing processes improved, eliminating the weak points that had caused so many catastrophic failures. By early 1939, the Merlin was ready. Not perfect, never perfect, but good enough. Production began ramping up just as German tanks rolled into Poland and the world descended into war once again. August 1940, the Battle of Britain. If you want to understand what the Merlin meant, you need to grasp what was at stake in those desperate summer months. The German war machine had crushed Poland in weeks. It had swept through France in a campaign so swift and brutal that it shocked the world. Now, Hitler's eyes turned toward Britain, the last obstacle standing between him and total domination of Europe. The Luftwaffe, flush with victories, launched a campaign to destroy the Royal Air Force and clear the way for invasion. Standing in their path were young pilots, many barely out of their teens, flying Supermarine Spitfires and Hawker Hurricanes. Both aircraft were powered by Merlin engines. When these fighters climbed to meet the German bombers, the sound of their engines became the sound of defiance itself. That deep, thunderous roar meant that Britain was still fighting, still resisting, still refusing to surrender. On September 15th, a date we now call Battle of Britain Day, the Luftwaffe threw everything it had at London. Hundreds of bombers, escorted by the best fighters Germany could produce, filled the skies. They expected to overwhelm the defenders through sheer numbers. What they encountered instead was a wall of Spitfires and Hurricanes that tore into their formations with a ferocity that stunned German commanders. By the end of the day, the Luftwaffe had suffered losses it couldn't sustain. The invasion of Britain was postponed, then quietly abandoned. The Merlin had won more than a battle. It had saved civilization, but the Spitfire was just the beginning of the Merlin's war. While the public focused on the elegant fighters defending British skies, the engine was quietly powering an entire fleet of aircraft that would reshape the conflict. The de Havilland Mosquito, built from wood and fabric in a desperate attempt to conserve strategic materials, became one of the war's most versatile aircraft. Twin Merlins gave it a top speed that let it outrun German fighters while carrying bombs deep into enemy territory. It could fly reconnaissance missions, strike targets with precision, and vanish before defenders could react. The Avro Lancaster heavy bomber mounted 4 Merlins on its massive airframe, creating a machine that could carry the war directly into the heart of Nazi Germany. These bombers could lift 22,000 pounds of explosives, enough to flatten entire city blocks. Night after night, Lancasters roared over German industrial centers, their Merlin engines drowning out the air raid sirens below. The strategic bombing campaign they enabled remains controversial, but there's no question it helped break Germany's ability to wage war. Perhaps the most remarkable Merlin story involves an American fighter. The P-51 Mustang started life powered by an Allison engine. It was fast and agile, but it couldn't perform at the high altitudes where bomber escorts were desperately needed. Then British engineers had an idea. What if they replaced the Allison with a Merlin? The result was transformational. Suddenly, the Mustang could escort American bombers all the way to Berlin and back, a feat that had seemed impossible just months earlier. This single modification changed the air war over Europe, allowing the Allies to strike targets deep in German territory with acceptable losses. But Britain faced a problem. Demand for Merlins was exploding, and Rolls-Royce simply couldn't produce enough engines. German submarines were strangling supply lines. British factories were being bombed. The mathematics were brutal. The RAF needed thousands of engines, but production could barely manage hundreds. Churchill faced a choice that must have felt like betrayal. Share Britain's most valuable secret with the Americans, or watch the war effort collapse. The deal with Packard Motor Company seemed straightforward on paper. The Americans would manufacture Merlins under license, using their vast industrial capacity to solve Britain's production crisis. Every blueprint, every specification, every hard-won engineering lesson would be handed over. It was industrial espionage in reverse, and it nearly failed before it even started. When British engineers arrived in Detroit carrying their carefully guarded secrets, they discovered a problem nobody had anticipated. British engineering drawings used imperial measurements, fractions of inches calculated to precise tolerances. American tooling operated on a different system entirely, working in thousandths of an inch. Every dimension had to be converted, every tolerance recalculated. A single mistake could result in engines that looked right but failed catastrophically under stress. The cultural clash went deeper than measurement systems. British craftsmen, trained in traditions stretching back generations, approached engine building as an art form. Each component was individually fitted, hand-finished to perfection. American workers, shaped by Henry Ford's assembly line revolution, believed in standardization and mass production. They wanted consistent quality at enormous scale. These philosophies collided with explosive force. The first Packard-built Merlins were disasters. Pistons seized during testing. Bearings failed under load. Cooling systems ruptured. American workers, accustomed to building automobiles, struggled with the precision demanded by aircraft engines. British engineers watched in horror as months of work seemed to evaporate. For a time, it looked like the entire program would collapse, taking with it any hope of American air power making a decisive difference. But something remarkable happened. Instead of giving up, both sides evolved. British engineers, forced to articulate knowledge they'd carried in their heads for years, discovered new ways to teach precision machining and quality control. American manufacturers introduced production techniques that British factories had never imagined. Slowly, painfully, the Packard Merlin emerged as something even better than the original. American metallurgy improved the alloys, making them stronger and more heat-resistant. Mass production techniques reduced the variations that had plagued hand-built engines. Quality control systems caught defects before they became failures in combat. By the war's end, Packard had produced over 55,000 Merlins, more than Rolls-Royce ever built. These engines powered the P-51 Mustangs that swept German fighters from the skies, making strategic bombing campaigns possible and hastening the end of the war. The collaboration between British precision and American industrial might become a template for Allied cooperation, proving that shared knowledge could multiply effectiveness. When the guns finally fell silent in 1945, the Merlin faced its greatest challenge yet: peace. Jet engines were clearly the future. Everyone said so. Propeller-driven aircraft seemed as obsolete as cavalry charges and wooden ships. The Merlin, for all its wartime glory, appeared destined for the scrapyard, a relic of a bygone era that had served its purpose and would now be forgotten. But the Merlin had other plans. Airlines discovered that Merlin-powered aircraft could carry passengers farther and more reliably than early jets, which were temperamental and thirsty for fuel. The Avro York, essentially a Lancaster bomber converted for civilian use, became the backbone of post-war British aviation, carrying mail, cargo, and passengers across routes that would have been impossible just years earlier. The most unexpected chapter came from air racing. Wealthy pilots and aviation enthusiasts discovered that surplus Merlins could be modified for speeds that defied imagination. These weren't just races. They were exhibitions of what human ingenuity could achieve when constraints were removed. Modified Merlins pushed aircraft to speeds approaching 500 miles per hour, setting records that stood for decades. Even now, more than 80 years after the first Merlin roared to life, these engines still fly. At air shows around the world, restored Spitfires, Hurricanes, Mustangs, and Lancasters take to the skies, their Merlin engines producing that distinctive sound, a deep, throaty roar that carries echoes of a time when everything hung in the balance. For those who hear it, the sound isn't just mechanical noise. It's a connection to history, a reminder of what was at stake and what was preserved. The Merlin's legacy extends far beyond the aircraft it powered. It changed how we think about engineering itself. Before the Merlin, perfection was often the enemy of progress. Engineers pursued ideal solutions that existed only on paper, unwilling to compromise even when compromise was necessary. The Merlin taught a different lesson. Sometimes good enough, delivered on time, matters more than perfect, delivered too late. The collaboration between Rolls-Royce and Packard established patterns of international cooperation that continue today. Modern aircraft engines, built by multinational corporations with components sourced from dozens of countries, owe a debt to those British engineers and American workers who learned to bridge their differences in the crucible of war. But perhaps the Merlin's greatest lesson is about human determination. The engineers who created it faced impossible deadlines and limited resources. They knew that failure meant not just corporate embarrassment, but potentially the enslavement of their entire civilization. Yet they pushed forward, working through exhaustion and despair, believing that their efforts mattered. The pilots who flew Merlin-powered aircraft into combat understood the risks. They felt the vibrations of components stressed beyond design limits, watched temperature gauges creep toward dangerous zones, and flew anyway because they believed in something larger than themselves. The Rolls-Royce Merlin wasn't just an engine. It was proof that ordinary people can achieve extraordinary things when everything depends on it. It was a symphony of metal and fire that helped save the world. And its roar, that unforgettable sound that once meant salvation for millions, still echoes wherever freedom is defended and remembered.